If you've ever asked in one of your linear algebra classes, when does this stuff ever get used? It's highly likely that you were told that there are applications in computer science, and particularly computer graphics. In video games, computer-generated movies, architecture, illustration, and more, you often have a scene where objects can move around and exist in a three-dimensional world. Linear algebra gives us the tools to describe the state of these objects and their movements. On the surface, this makes sense because we can think of matrices as transformations of space, which one might imagine would be useful for describing the state of 3D objects to a computer. But what kind of matrices do we use for scaling, rotating, and translating objects? Are we sure that matrices are the best tool for the job? When we try to implement this idea, we'll run into some obstacles that you may not expect. In this video, the plan is for you to come out understanding how you could describe the scale, orientation, and position of 3D objects using the language of linear algebra. I should mention, by the way, that to get the most out of this video, you're going to need to know the very basics of linear algebra, and in particular, matrices. If you don't feel comfortable with those topics right now, I would highly recommend you watch 3 Blue 1 Brown's excellent series on the topic, The Essence of Linear Algebra. Particularly, chapters 3 and 4 are going to be helpful for what we're talking about today. Before chugging along with the video, I think it's important to consider why matrices should even be used here. Why not use some other system, like complex numbers? First of all, matrices generalize really well to transformations in both 2 and 3 dimensions. This way, we can use similar techniques when rendering in 2D or 3D, and it can save us a lot of headaches. Also, the act of describing the way an object is situated in space can, with linear algebra, be expressed in a single operation. Specifically, we can represent translation, rotation, and scaling as separate operations and multiply the matrices together to create one combined transformation matrix, which can then be sent over to a graphics processor. So now that we're convinced that we want to use matrices for our graphics application, we need to figure out exactly how we're going to use them. To make our lives easier, we're going to start in 2D and only then move on to the more complex 3D case. Let's start by finding a matrix to represent scale. We can do this by independently scaling each of the basis vectors and looking at where they land to create the corresponding matrix. Here are some examples of this being shown visually. To transform a shape using this matrix, what we do is apply the transformation to each vertex represented by a vector. Now for rotation. We start with the 2 basis vectors as always. They both need to rotate the same amount by some angle theta. After this, they'll land at some new points, and those are going to be the columns of our matrix. We need a way of calculating these points. Let's start with I hat. If we draw a perpendicular line segment connecting I hat to the x-axis, we can form a right-angled triangle which has a hypotenuse with length 1 and an angle with measure theta. Then, using some basic trigonometry, we see that I hat lands at the coordinate cosine theta sine theta. We can do something similar for j hat. We can note that since I hat and j hat are 90 degrees apart from each other, then this angle must be 90 minus theta. It also then follows that this other angle must be theta. Then, using the same kind of reasoning, we see that j hat is at the coordinate negative sine theta cosine theta. And so our final matrix looks like this. Alright, so that's been pretty easy so far, and now all that's left to do is translation. But the astute among you may realize that there's a pretty big problem we're about to run into if we're going to try to represent translation as a matrix. This is because one of the fundamental rules of linear transformations is that the origin must stay fixed in place. But what we want with the translation is to slide the entire plane, meaning necessarily the origin would have to move. So it seems like we could never represent translation through linear transformations. But the truth is, we actually can do it. We just need to get a better view of the full picture. What we can do is imagine our plane as part of a greater 3-dimensional space where it sits one unit above the xy plane. This way, the origin is no longer part of the plane we want to translate, and so we can slide it in both the x and y directions using a 3-dimensional shear transformation. If we only consider the x and y coordinates of the resulting vectors pointing to the vertices of our shape, then we've effectively done translation as linear transformation. Isn't that cool? A three-dimensional shear is represented by this matrix here, which looks almost like an identity, except our third basis vector is slanted in the direction of our desired translation. In order to use this new 3D transformation, it naturally follows that the coordinates we use to represent our object will have to be 3D vectors as well. These are what are known in the business as homogeneous coordinates. They're really similar to our regular coordinates, except we consider that they are situated 1 unit above the xy plane and so have a z coordinate of 1. Also, our rotation and scale matrices will have to be updated to accommodate our new homogeneous coordinates. In both cases, we'll just have the original matrix in the top left and then fill out the rest, considering that the third basis vector shouldn't be affected by rotation or scaling, and the original two basis vectors should never leave the xy plane. So in the end, it just looks like the original 2D matrix pasted in the corner of a 3D identity matrix. Now that we have all of our matrices, we can multiply them together to get our complete transformation describing the object's scale, rotation, and position in space. There is some technical detail to consider here though. Recall that with matrix multiplication, order matters, and so we need to think about what order we want to do our transformations. Our desired order is scale first, then rotate, then translate, and so our final product will look like this. If we apply the resulting matrix and watch from our 2D view, we should see all the transformations happening at once in a beautiful mathematical symphony. At this point, we've successfully tackled performing 2D transformations with matrices. However, many applications need to perform this operation for 3D scenes. Let's try to use what we learned from the 2D transformations to now understand how we could perform something similar in 3 dimensions. Starting again with scale, all we need to do is scale the 3 basis vectors independently and then record their resulting positions as the columns of a 3x3 matrix. Rotation is a little more complicated, as we now have 3 axes to perform the operation around, meaning we'll have to create 3 separate rotation matrices to perform each step. But you should be able to confirm to yourself that these 3 matrices represent rotation about the x, y, and z axis respectively, using the same logic we used for the 2D case. When we try to do translation, we run into the same problem that the number of dimensions is not enough. It is not possible to shift our 3D grid while keeping the origin fixed in place. Just like before, when we needed to imagine our 2D space as a plane in a 3D world, we now need to imagine our 3D space as a slice of a larger 4-dimensional universe. You probably can't visualize that, and I sure as hell can't animate that, but luckily, the intuition is the exact same as before. What we need to do is imagine the various 4D shear transformations, which will look like translations from our 3D view. And just to be clear, we're imagining our 3D space as lying 1 unit along the 4th dimension, so that the shear has a similar effect to what we did for our 2D translations. Right now, what you're looking at are some examples of these 4D shear matrices, and the corresponding sliding effect they have when we look at it from our 3D view. This means that again, we're going to need to use homogeneous coordinates, where the 4th component of each coordinate, commonly referred to as w, will be set to 1. And as we are now using 4-dimensional coordinates, our scale and rotation matrices need to be updated in a similar way to the 2D transformation case. Before moving on, try to make sure that the way we're expanding these matrices really makes sense intuitively. And now, we can fill out our matrices with whatever values we want to use for our transformation, and then multiply them all together to get our final transformation matrix. And just as a quick sanity check, if I do apply this final transformation matrix to this torus, we see that the resulting transformation is exactly what we expected. So that's it. With just a little thinking out of the box, or out of the dimension, we were able to represent any object's scale, rotation, and position using only a single matrix. Isn't that cool? And not just cool, if you're interested in computer graphics at all, then chances are you'll be using this sometime in your future. But computer graphics wasn't the only thing we learned from our journey here. Hopefully, now, if you're ever sitting in a math class thinking about when you'll use a seemingly obtuse and abstract topic, you can be reassured that oftentimes there are some pretty interesting and useful applications out there if you're willing to look for them. The other key takeaway is that four-dimensional math can actually be really useful despite us not living in 4 dimensions. Mathematicians care about 4D math because it can, counterintuitively, be an extremely powerful tool for understanding our 3-dimensional world.